Okay, so I'll get started here. This is Mike Cushman at InfoSciTech. We're doing the final project summary for WP1763, which is shelf-stable epoxy repair adhesive. So just briefly talk about the project team. It was principally performed here at InfoSciTech. I was the PI. Jim Belcher was co-technical lead, program manager, and Matt Reed, who's sitting here with us as well, did the lion's share of the technical work in the laboratory. And then a major subcontractor for us was Thies Technology, who was focused wholly on, their activities were solely focused on microencapsulation, and we'll touch base on that. And then Frank Bruce at AFRL at Hill Air Force Base provided us with some pretty useful insights throughout the course of, I guess, the later stages of the program as we were trying to vector it correctly to kind of get situated for the next phase. And I'm going to hand it over to Jim Belcher, who's going to brief the summary slides from slide 3 forward.
Okay. Thanks, Mike. So this project started in 2010 and just wrapped up. The original statement of need is listed there, WPSON 0907. But really, to put the problem statement out there in today's context is that a lot of the repair adhesive that's used at military installations for composite and metal-to-metal repair expires prior to use. And as a result, you're left with a partially reacted, hazardous adhesive product that needs to be disposed of. So one of the assessments was that it was over half of that material was expiring before it could be used. And as a snapshot for quantities, this year, over a 6-month period, just at 2 logistics centers, 1,600 pounds of one-part epoxy adhesive was purchased, which, if you carry that through, would mean 800 pounds of excess hazardous waste just from those 2 locations alone. So extending that, the Air Force has lots of partial deliveries and issues with procurement that result in excess material being purchased that they're not able to use. And then the Army, a lot of forward operating facilities that do repair work, the logistics and overhead burden of supplying those facilities with adequate refrigeration, storage facilities, and other required equipment for the unstable single-part adhesive is quite burdensome and requires a lot of excess resources to maintain. So that's a bit of background on the problem. So now we're going to get into what we tried to accomplish and what our technical objectives were for this project. So our objective was to extend the processing window for single-part adhesives, specifically epoxy adhesives. And the graphic at the bottom of this chart shows just a notional cure profile. So with a single part material, it's reacting from the second that it's fabricated at the OEM. And what you want to do is prolong the latent cure stage, which is the initial part of the cure cycle where your material is not reacting quickly and is essentially in a storage type condition. But once you pass a threshold and you begin to cause a chain reaction with the cure components, you start a rapid cure stage. So what we want to do is prolong the latent reaction stage. So what you see here in this graph is a standard adhesive where the latent cycle is rather short, and the SSA, or shelf-stable adhesive, has a longer latent cure component. So what this is going to accomplish for the end user is a reduced amount of hazardous waste being generated at airfield repair centers. It's going to reduce or eliminate the dependency on freezer or refrigerator storage by enabling ambient condition storage. And then there's a number of other commercial applications that this type of technology could be leveraged for, higher temperature curing, for high temp composites, things of that nature. So I was talking a bit about the cure mechanisms here, and so I'm going to get into a little bit more detail on this slide. Without a accelerator component, your epoxy adhesive requires high temperature and long cure times, which is not conducive or compatible with the composite materials that are currently in use. So by adding a accelerator molecule, you're able to reduce the cure time and reduce the temperature. So what you see on the left is what the excessive heat and time requirement for the polymerization reaction, and on the right is a notional description of what the cure cycle would look like with an accelerator incorporated into the formulation. So most single-part epoxy adhesive formulations use an accelerator. So we focused on those formulations that use an accelerator in this project. So the approach here is to encapsulate the accelerator with a polymer shell. And previous efforts have looked at encapsulating different parts of the reaction process, for instance, encapsulating the catalyst. By encapsulating the accelerator, it is effectively controlling a reaction much earlier in the process, so there's less side reactions going on as over a long period of time. So we didn't modify the curative chemistry at all. We used all the same accelerators, all the same catalysts, resin systems. We just added an inert polymer shell around the accelerator. So that hopefully will reduce the amount of time to bring this technology to market. Let's see. So by adding the barrier around the accelerator, it creates another way to control the kinetics of the reaction by reducing the amount, or by prolonging the amount of time required for the urone to react with the other components in the resin system. So we had a few approaches on how to encapsulate the accelerator. One approach was a natural polymer shell, and then we had another conformal coating that we were evaluating, and that had the benefit of having a higher mass loading of active material. The problem there was having a dense enough shell that was contiguous, so that there wasn't any partial exposure of the accelerator particle to the resin. So it was a bit more attractive, but in the end we weren't able to formulate a good shell with the conformal coating, and we were able to get a nice, thick, consistent shell with our natural polymer approach. And that approach used microencapsulation via complex coacervation. So we're getting into now a bit of the process we use to develop this system. And since we are not a OEM supplier of the adhesive, we didn't have access to the full formulation for the adhesives, and we also didn't want to get into that variability. So we created a simplistic adhesive formulation that used all of the major components of the fully formulated single-part adhesive. So you've got primarily it's epoxy resin. We used an Omnicure catalyst, and then we looked at several different accelerators, and we did finally settle on the Fenuron accelerator, and then the fumed silica added inert additive. And those formulations, we made both paste formulations that were used without creating films, and then we had a film variant that we pulled into films with a fiberglass scrim. So we had 3 stages of testing whenever we were looking at a new formulation of microcapsules. So the bulk of the development and evaluation was looking at different encapsulated Fenuron batches and evaluating the encapsulation process. So I think we had about on the order of 50 different capsule batches fabricated, trying to optimize the process and the encapsulation conditions. So when we evaluated the microcapsules themselves before we added them into the formulation, we looked at them with optical and scanning electron microscopy to ascertain the aspect ratio of the coated particles and just get a visual assessment of the encapsulation efficacy. After that, we performed differential scanning calorimetry to assess the percent activity of the microcapsules, and it effectively told us what how thick the shell was around each capsule, around each accelerant particle. The paste formulation stage of testing formulated the encapsulated accelerant with the simplified adhesive formulation that we mentioned on the previous slide, and put it in a viscometry setup. So it was essentially a viscometer cup with a spindle spinning at extremely low rotational speed, and the cup was maintained at 60 degrees centigrade. And as the reaction kinetics as the reaction occurred, the viscosity of that formulation started to increase and rapidly cured at the end after the latent cure stage had passed. And so I'm going to show on following slides examples of all of these data sets, and we can talk a bit about that at that point. And then finally, and this is where the bulk of the testing was conducted, was with the films. So after the capsules were vetted and down selected in the first stage, we ascertained good viscometry data from the paste formulations. We would make films with hot melt drawn hot melt setup. So those samples we used for strength testing at our facility here at InfoSytex. Primarily that was single lap shear testing at ambient temperature. We did a number of tests with those samples. We stored the adhesive prior to curing for an extended period of time, and then we exposed the samples to some conditions after they were cured, and we analyzed them with a mechanical tester where the testing was conducted at ambient temperature. And after the down selection process past that stage, we took our final composition and our final formulation and sent it to a third party for a full workup of mechanical analysis. Initially, right after the samples were cured, there was a full set of data gathered. And then after a series of different simulated aging environmental exposures, they were tested again to verify that the adhesive wasn't deleteriously affected by incorporation of the polymer shell into the formulation, because chemically that is the only difference in the formulation. So getting back to our microcapsule results, here's an example of our microcapsules. We typically wanted fairly round capsules, more oblong or higher ratio. Particles tended to have thinner shell material on the end, and it resulted in pore barrier properties and thus reduced shelf life. And so this quickly became a QC method as we became more proficient with the encapsulation approach for this particular formulation. And then we looked at DSE, as I mentioned, to determine the activity of each encapsulated batch. And a typical activity was about 55 to 57% by weight. And that was fairly consistent as we got later on into the project, and the encapsulation process became more consistent. So this slide, let's talk about a bit of the paste formulation testing. So the graph you see on the right here shows the viscosity profile for a number of formulations. The black line is our four-part single or our simple epoxy formulation with regular Fenuron accelerant incorporated. So there's no encapsulant around the Fenuron for the black line. So that shows that after about 30 hours at 60 degrees centigrade, the latent cure stage passed, and it went into full onset of cure, and it rapidly cured and became a hardened epoxy batch. So the other experiment, or the other graphs here show successive iterations of our capsule formulation. So the purple line showed an early on formulation, shows a small improvement in the elongation of the latent cure cycle. The blue line shows an even better example of the improved stability of the formulation. And then what we finally wound up with was a formulation that would not cure at 60 degrees centigrade in the viscosity cup. The two green lines that you see on the bottom that look flat actually went on for over 600 hours, and we had to stop the test because they just weren't curing. So that was the formulation that we wound up transitioning to and down selecting for further investigation. We're going to talk about that here on this slide. So this table here shows just a snapshot of some data, some DSE analysis here, and what this translates to is a pretty consistent percent activity of around 56% by mass. So that part of it was consistent. And then we had our viscosity analysis, and as you can see, the unencapsulated Fenuron was curing after about 35 hours. The next formulation below lasted 166 hours, and then formulations beyond that all lasted significantly longer, and we had to stop the test after a certain number of hours. So then we needed to verify that these modified formulations with an encapsulated accelerant would still cure as they needed to during a a typical cure profile for doing a repair process. And they needed to maintain the mechanical strength that the initial formulation had without any encapsulant. So the unencapsulated Fenuron had a single lap joint strength of about 2,400 psi. And then that initial sample that you see below that ends with A3 had a reduced lap joint strength. So we needed to modify the formulation slightly. And when we made that modification, we found that the mechanical strength was much more commensurate with what the unencapsulated Fenuron was doing. So samples that end with 111 through 114 all contain encapsulated Fenuron. They all have consistent DSC parameters. They all have significantly improved shelf stability test results from viscosity analysis, and they have equal or higher mechanical strength. So those three check boxes allowed us to move to the next phase of testing, and that was looking at actual stability tests characterized by mechanical evaluation. So on this slide here, we'll start with the graph on the left. The baseline formulation, the blue line, shows what the mechanical strength or show the profile for shelf stability of the unencapsulated Fenuron. So after about 20 hours, the unencapsulated Fenuron batch wouldn't, you couldn't even really create a sample. So it was stored at 20 hours prior to cure at elevated temperature. So after 20 hours, we took the sample out, cured up the lap shear sample, and tried pulling it. And there was almost no resistance. It broke right apart. So the shelf stability at 60 degrees centigrade for the single part adhesive is somewhere significantly less than 20 hours. Now, in contrast, when you look at the two different formulations that we tested that incorporated shelf-stable adhesive, that is, having the encapsulated Fenuron, you see a much different story. You see that the strength after the uncured adhesive was stored for a long period, the mechanical strength was still retained when it was pulled. And these were all conducted with sample sets of 9 specimens each. So there's a high degree of confidence in this data. So after this test, which again I think the longest we tested for was about 200 hours, we are ready to do an unaccelerated shelf stability test. So in the graph you see on the right, we put a number of samples in a environmental chamber, held it at 90 degrees Fahrenheit, and left it there for 2 years. We took samples out periodically and tested them, and after about 3 months, the unencapsulated Fenuron, the baseline, which you see in the green line, started to cure, and the vast majority of the mechanical strength had diminished. The shelf-stable variant, you see in the blue line, had a much better stability for a year. And at some point after a year, we actually didn't put enough samples in. We didn't think it was going to last that long. At some point between a year and 2 years, the samples did indeed lose their mechanical strength, but still it's a significant improvement over the unencapsulated Fenuron, and it does show that the test is an accurate way to assess them. So at that point, we took our final formulation and began to do a full workup on them. And so this formulation, we created, do you remember how many sheets of film we made, Matt?
Probably a dozen to make up everything.
Yeah, so we had, I would say, on the order of 100 square feet of adhesive film that we fabricated. to conduct this test. And it involved single lap shear tests, climbing drum tests, 3-point sandwich flex tests, double lap shear, flat-wise tensile testing. And all of these tests, we made samples of a baseline formulation with unencapsulated Phenuron and a shelf-stable variant with encapsulated Phenuron. And we compared those two for each of the test conditions. So the initial control was just testing films that were cured fairly soon after they were fabricated. So there was no extended storage, no post-cure aging. So they were cured right away and evaluated at ambient conditions. And by comparison, the encapsulated Phenuron and unencapsulated Phenuron samples all had very similar data. So there was no detriment with the capsule material in the control tests. And that was the case for all of the other tests. As you can see, there was a pass condition. And what that means is that there was comparable or better mechanical results compared to the baseline. So the next series of tests was testing cured coupons at extremely cold temperatures and extremely hot temperatures. There was good results there. And then accelerated aging, where they were exposed to various humidity and elevated temperature conditions for an extended period of time, 90 days. And then there was testing at ambient and testing at, again, the hot condition. And then high humidity accelerated aging just looked at testing for a shorter period at a higher relative humidity and testing at ambient conditions. And that was all conducted at as I mentioned, a third-party testing facility, Intertech in Pittsfield, Mass. So that's the synopsis of our technical data. Some of the benefits of this system include, for DoD that is, improved sustainability. That is going to be an immediate outcome of this, as is reduced hazardous waste. So those are the two major drivers for this work, is to reduce the environmental burden that the DoD repair operations have. Specifically for the Air Force, we're going to have significantly less expired adhesive, as I mentioned before, reduced logistical burden to maintain the refrigerated facilities and transport the larger than required number of adhesives for the forward repair facilities. And that's going to be the case also for the Army. And then the expansion of a universal repair toolkit is something that they've been working towards, and this is going to be another tool in that shed to help achieve that goal. And we haven't been incorporating input from the Navy as of yet. That's something we intend to do in the near future, but we envision similar benefits for that armed force as well. So as far as technology transition goes, the next step for this technology is to validate the formulation in commercial formulations, so incorporate the encapsulated accelerant into the fully formulated adhesive. And we don't anticipate any issues there, since all of the primary components have been vetted in the CERTIP program. And once that's completed, incorporating and validating that the adhesive material can be worked in typical standard layup procedures for both field repair and repair in the depots. That's going to be conducted. And finally, flight testing. So actually do some field repair or some repair in the logistics centers on aircraft primary and secondary structures and evaluate their performance after typical operational use. So we've teamed up with Boeing, the C5 program office, and a UAS program office for the Gray Eagle with the Army to try and accomplish this. So conclusions, summary. One thing I didn't touch on was our scale up. We are still operating at a moderate scale. The weight percent for these capsules is small, so 75 gram batch will produce a large amount of adhesive. So 75 grams of capsules will be about 2 pounds of adhesive. So there's a lot of, it's a small constituent of the full formulation. Repeatability, we were able to get good repeatability at the small scale, but actually we really wanted to focus on our repeatability analysis at the larger scale, the 75 gram batches, because that's where some consistency issues have been found in previous efforts, and we were able to produce our first 5 75 gram batches extremely consistently with good stability, thermal properties, and mechanical properties. The mechanical integrity, that was a key finding of our full workup mechanical testing at the third party. Until then, we hadn't been able to determine if the capsules would have a deleterious effect when exposed to humidity, and it was very convincing that the polymer shell does not impede on the formulation's good humidity and moisture resistance. The TRL assessment of the technology is currently at a 5. And then the conclusions here are all items that we've gone through. We've got a vast improvement in shell stability. So after a year at 90 degrees Fahrenheit ambient temperature, our shell-stable adhesive still retains 75% of its initial adhesive strength, where after 3 months there was no strength left with the unencapsulated Veneron. And that is a marked improvement and can really be a game changer for supply logistics for repair facilities. So following that, we've got one of the publications here that was released back in 2012 at SAMPE Tech, and I believe that's the last slide. So if there's any questions, I think we'll take those now.
Sure, this is Robin. So one of the comments had to do with the total one of the comments on the follow-on, the ESTCP follow-on, had to do with the total quantities of adhesive and the amount that is being disposed of. And I think it would benefit to try to search for Army and Navy logistics centers as well and see if they had similar higher, lower needs and what their disposal is like.
Yeah, absolutely. It's been a really difficult thing to assess. We've probably spent the last year looking for those numbers. There was a sort of program in the late 90s to try and assess a lot of those numbers, and they had limited success with it. There was a lot of assumptions made. So I think what we can do in the future is have try and incorporate a tracking tool and see if that can be an effective way to do an evaluation.
Or if you guys have any contacts that you think would be beneficial for us to reach out to, we certainly could do that as well.
Okay, well, we can do some of that for sure.
Okay.
And then just technically, I noticed that actually some of your lap joints were, to the point where they really were a little bit stronger than the control. Any explanation for that, or is it just in the noise in terms of that measurement?
From what we saw, it's probably just kind of within the noise. We did large batches of these because we saw sometimes a fair bit of variation. So a little bit of a swing here or there, we were kind of considering to be in the noise.
And then one additional question has to do with, let's say, a supplier or someone who would actually manufacture. Have you had any discussions with or considered where you might go to actually get someone interested in producing a shelf-stable epoxy?
Yeah, we as far as the encapsulation of the accelerant itself, we're lined up, and Feast has a facility where they'll be able to scale up. And now we've had conversations with both Hinkle and SciTech with respect to the actual adhesive itself, and I think they're waiting for us to get a little bit more momentum behind the program and move to the next stage before they really sign up to it. But we have ongoing conversations with both those companies.
Okay, sounds good. And to anyone else on the phone, are there any other questions, comments, thoughts? Okay, with that, I want to thank you for presenting and for your work on this project.
All right. Well, thanks. We appreciate the support.